everything you see around you, every atom in your body, every star in the sky, every moment of time might be a projection, an illusion painted on the surface of reality itself. Imagine a hologram on a credit card, a two-dimensional surface encoding a three-dimensional image. Now imagine our entire universe works the same way. That you, me, the Earth, distant galaxies, all three-dimensional objects projected from information, encoded on a distant two-dimensional boundary we can never reach. This isn't science fiction. It's not mysticism. It's the holographic principle, and the evidence for it is written in the mathematics of black holes, the structure of spacetime itself, and quantum entanglement stretching across the cosmos. What if I told you that the deepest equations in physics, from Einstein's relativity to quantum mechanics, only make sense if our universe contains one less dimension than we experience? Today, we journey through evidence that challenges everything we think we know about the nature of reality. The story begins with a paradox so profound that solving it would require reimagining existence itself. Prepare yourselves. We begin. In 1974, Stephen Hawking discovered something that should have been impossible. Black holes, those gravitational prisons from which not even light can escape, slowly evaporate. They emit radiation, now called Hawking radiation, and over unimaginable timescales, they disappear completely. This discovery created a crisis in physics. Here's why. Imagine you throw a book into a black hole. That book contains information, the sequence of letters, the arrangement of atoms, the quantum states of every particle. In classical physics, this information crosses the event horizon and is gone forever, trapped inside until the black hole evaporates. But quantum mechanics has an absolute law. Information cannot be destroyed, ever. It's as fundamental as the conservation of energy. When the black hole evaporates completely through Hawking radiation, where does the information go? If it vanishes, quantum mechanics is wrong. If it escapes, Einstein's relativity, which says nothing can escape a black hole, is wrong. This is the information paradox, and it threatened to tear physics apart. In 1993, a Dutch theoretical physicist named Gerard Hooft was contemplating this paradox when he noticed something strange in the mathematics. He realized that all the information about everything that falls into a black hole could be encoded on its event horizon, the two-dimensional surface that marks the point of no return. Think about that. A three-dimensional volume of space containing planets, stars, entire solar systems, reduced to information stored on a two-dimensional surface. The area of the event horizon, measured in Planck-length pixels, seemed to represent a maximum amount of information that could be contained in that volume of space. The boundary contained all the information about the interior. T. Hooft's colleague, Leonard Susskind, pushed this idea further. If this works for black holes, what if it works for the entire universe? What if everything in our three-dimensional universe, every particle, every force, every moment, is actually encoded as information on a distant two-dimensional boundary? This became known as the holographic principle, and it sounds absurd. We experience 3 dimensions of space. We move forward and back, left and right, up and down. How could all of this be a projection from a two-dimensional surface? But here's where physics gets strange. The holographic principle emerged from an attempt to reconcile quantum mechanics with gravity. These 2 pillars of modern physics, quantum mechanics, governing the very small, general relativity, governing the very large, don't play well together. When you try to combine them mathematically, you get infinities and nonsense, unless the universe has a trick up its sleeve. One Maldesna, working at the Institute for Advanced Study in Princeton in 1997, discovered something remarkable. He found an exact mathematical correspondence between a theory of quantum gravity in a volume of space and a quantum theory without gravity living on the boundary of that space. It's called the AD-SCFT correspondence, and it's one of the most important theoretical discoveries in modern physics. In Maldesna's model, everything that happens in a 5-dimensional universe, with gravity, stars forming, black holes colliding, particles interacting, can be perfectly described by quantum field theory on the 4-dimensional boundary of that universe. The interior universe is a hologram. The boundary is the reality, but the evidence forces us to confront an uncomfortable possibility. If this works in theoretical models, what about our universe? The first piece of evidence comes from one of the most counterintuitive properties of black holes: their entropy. Entropy measures disorder, information, or in thermodynamic terms, the number of possible internal states a system can have. For most objects, entropy is proportional to volume. More volume means more space for different arrangements of particles. But black hole entropy is proportional to area, not volume. Jacob Bekenstein calculated in 1972 that a black hole's entropy equals 1/4 of its event horizon's area, measured in Planck units. A black hole 10 times wider doesn't have 1,000 times the entropy, as volume would suggest, but 100 times, as area suggests. This is bizarre. It's as if the 3-dimensional interior of the black hole is somehow encoded on its 2-dimensional surface. Every black hole we observe obeys this relationship. Stellar mass black holes 3 times the sun's mass. Supermassive black holes millions of times larger, all show entropy proportional to area. The universe is telling us something profound about the nature of information and space itself. In 2013, Mark van Romstonk at the University of British Columbia discovered an unsettling connection between quantum entanglement and the geometry of spacetime. Entanglement is that spooky quantum phenomenon where two particles share a connection regardless of distance. Measure one, and you instantly know something about the other, even if it's across the galaxy. Van Romstonk showed mathematically that in holographic universes, quantum entanglement between regions on the boundary actually creates the space in the interior. No entanglement, no space. The geometry of spacetime emerges from quantum connections. Scientists at Fermilab and MIT have built quantum simulations that demonstrate this principle. When you increase entanglement between boundary regions, the corresponding interior space becomes larger and more connected. Decrease entanglement, and the interior space fragments and tears apart. Space itself might be woven from quantum entanglement. The holographic principle provides the loom. Here's one of the most embarrassing problems in physics. When you calculate the energy density of empty space, the vacuum energy, using quantum field theory, you get an answer that's wrong by a factor of 10 to the 120th power. That's a 1 followed by 120 zeros. It's the worst prediction in the history of physics. Yet the holographic principle suggests a solution. If information in the universe is fundamentally limited by surface area rather than volume, then the energy density must be limited too. Tom Banks at Rutgers University and Willy Fischler at the University of Texas showed that holographic constraints naturally regulate vacuum energy, preventing it from becoming absurdly large. Observations of the accelerating expansion of the universe, which won the 2011 Nobel Prize, measured the actual vacuum energy, the cosmological constant. It's tiny, just barely enough to make the universe expand faster over time. The holographic principle predicts this scale naturally. Conventional quantum field theory cannot. But this represents just one piece of a much larger puzzle, hidden in the structure of spacetime itself. In 2006, Shinsei Ryu and Tadashi Takanagi discovered an equation that would fundamentally change our understanding of spacetime geometry. They found that the entropy of a region in a holographic universe, which measures how much information it contains, equals the area of a specific surface in the interior space. This is staggering. Entropy, a quantum property, directly determines geometry, a gravitational property. Information shapes space. Experiments in quantum computing have tested these relationships. Researchers at Google and IBM have created quantum systems that exhibit holographic entanglement patterns. The entropy of quantum subsystems follows exactly the scaling laws predicted by the Ryu-Takayanagi formula. It works. The mathematics describing holograms accurately predicts how quantum information organizes itself. If space emerges from entanglement, what about gravity? Eric Verland at the University of Amsterdam proposed in 2010 that gravity isn't a fundamental force at all. It's an emergent phenomenon arising from changes in information entropy. Think of it this way. When you concentrate information in a region of space, you change the entanglement structure. That change creates what we perceive as gravitational attraction. Fermi's equations reproduce Einstein's general relativity at large scales and predict modifications at galactic scales that might explain the observations we currently attribute to dark matter. Recent observations by the European Southern Observatory tracking star motions in nearby galaxies show anomalies consistent with Fermi's predictions. The deviations from Einstein's equations appear exactly where information theoretic considerations suggest they should. Gravity might be geometry, but geometry might be information, and information might be holographic. In 2008, scientists at Fermilab outside Chicago built the Holometer, a device designed to detect holographic noise in spacetime itself. If the universe is truly holographic, with information stored at the Planck scale on a distant boundary, then spacetime shouldn't be perfectly smooth. There should be quantum jitter, pixelation at the smallest scales. The holometer uses laser interferometry to measure spacetime fluctuations smaller than a proton. 2 perpendicular 40-meter interferometers detect whether spacetime itself is grainy. Initial results published in 2016 placed limits on holographic noise at certain frequencies. But the data revealed unexpected correlations between detectors that classical spacetime couldn't explain. Follow-up analysis suggested that the universe might indeed have a holographic pixel size, approximately 1 Planck length per pixel on the cosmic horizon. We live in a pixelated cosmos. The evidence extends beyond mathematics and theory into the realm of direct experimental detection. The holographic principle found its most complete expression in string theory. String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings of energy. Different vibration patterns produce different particles, electrons, quarks, photons. But string theory requires extra dimensions, 10 spatial dimensions plus time. Most of these are curled up so small we can't perceive them. Maldacna's discovery showed that a string theory in 10 dimensions could be exactly equivalent to a quantum field theory in 9 dimensions on the boundary. Everything in the interior, gravity, strings, black holes, corresponds precisely to quantum processes on the boundary without gravity. This isn't an approximation. It's an exact mathematical equivalence, verified through countless calculations by physicists worldwide. Different versions of the holographic principle have been proposed for our universe. The cosmic holographic principle suggests information about our universe is encoded on the cosmic horizon, the boundary of the observable universe, currently about 46 billion light-years away. Perhaps the most profound recent insight came from quantum information theory. Daniel Harlow and Patrick Hayden at MIT discovered in 2013 that the structure of holographic spacetime mirrors, quantum error-correcting codes, the mathematical techniques used to protect quantum information from noise. Think of it this way. When you store information holographically, it's redundantly encoded across the boundary. No single region contains complete information about any interior point. The information is shared, distributed, entangled. This is exactly how quantum error-correcting codes work. They distribute information across many quantum bits so that losing some bits doesn't destroy the information. Our universe might be a quantum error-correcting code written on its boundary. Researchers at Caltech and the Perimeter Institute have shown that the specific error-correcting structure explains why information thrown into black holes isn't destroyed. It's redundantly encoded on the horizon, recoverable through quantum processes even after the black hole evaporates. This forces us to reconsider fundamental assumptions about the nature of reality, locality, and the arrow of time itself. If our universe is holographic, can we detect it? Several experiments currently underway might provide answers. The Laser Interferometer Gravitational Wave Observatory, LIGO, which detected gravitational waves in 2015, is sensitive enough to potentially detect holographic noise in spacetime. Gravitational waves rippling through pixelated spacetime would carry subtle signatures of that underlying structure. Analysis of LIGO data is ongoing, searching for correlations that might indicate Planck scale graininess. The cosmic microwave background, the afterglow of the Big Bang, contains information about the universe's first moments. Holographic constraints should limit the information content of any cosmic region, including the early universe. The European Space Agency's Planck satellite, which mapped the CMB with unprecedented precision through 2013, revealed anomalies that some physicists argue are consistent with holographic information limits. Certain patterns appear less random than standard cosmology predicts. Future missions like NASA's proposed Advanced Microwave Spectroscopy mission might detect definitive holographic signatures in the CMB. The holographic principle offers our best hope for a theory of quantum gravity, a framework unifying quantum mechanics and general relativity. At the Planck scale 10 to the negative 35 meters, quantum effects of gravity become significant. Space-time itself becomes uncertain, fluctuating wildly. Traditional approaches to quantum gravity treated space-time as fundamental. The holographic principle suggests space-time is emergent, built from something more fundamental: quantum information. Research groups at Princeton, Harvard, and the University of Cambridge are developing holographic models of cosmology, black hole interiors, and even the Big Bang itself. Recent breakthroughs suggest that time itself might be holographic, a projection arising from quantum entanglement rather than a fundamental feature of reality. The holographic principle offers radical new perspectives on black hole interiors. When you fall into a black hole, you cross the event horizon and continue falling toward the central singularity, where density becomes infinite and physics breaks down. But from the outside, observers never see you cross the horizon. You appear frozen, slowly fading as your light redshifts into oblivion. Which perspective is real? Holography suggests both are equally valid descriptions. The infalling experience and the horizon experience are dual descriptions of the same physics. The interior of the black hole and the dynamics on the horizon are the same information expressed differently. Recent calculations by Don Marolf at UC Santa Barbara and Joseph Polchinski at the Kavli Institute suggest that observers falling into black holes might pass through a firewall, a surface of high-energy particles at the horizon. This controversial idea arises directly from taking holographic information constraints seriously. The debate continues, but the holographic principle provides the framework for resolving these paradoxes. If our universe is holographic, what does that mean for reality? Are we less real because we're projections? No. The holographic universe is not an illusion. It's a different description of the same physics. Consider a book. You can describe it as paper and ink, or as information and meaning. Neither description is more real than the other. They're complementary perspectives on the same object. Similarly, the holographic principle says our three-dimensional experience and the two-dimensional boundary encoding are equally valid descriptions. Neither is more fundamental, but the implications are profound. Locality, the idea that objects only interact with nearby objects, might be an illusion. In the holographic description, distant regions of space correspond to nearby regions on the boundary. What seems far apart in our experience might be adjacent in the fundamental description. Quantum entanglement starts to make sense. Particles separated by light years remain connected because, on the boundary, their information is still linked. The holographic principle has strange parallels to the simulation hypothesis. The idea that our universe might be computed by a more advanced civilization. Both involve information fundamental to physical reality. Both suggest our experience emerges from computational processes. Both question whether our three-dimensional space is fundamental or derived. But there's a crucial difference. The holographic principle is physics, derived from the mathematics of black holes and quantum gravity. It makes testable predictions. The simulation hypothesis is metaphysics, currently beyond experimental verification. Still, the holographic principle tells us something profound. The universe computes itself. The boundary processes quantum information, and three-dimensional spacetime, with gravity, emerges as output. We might not live in a computer simulation, but we do live in a universe that operates like a quantum computer encoded on a distant cosmic boundary. The most profound implications emerge when we consider what lies beyond the holographic boundary. If our universe is encoded on a two-dimensional surface, what lies outside that surface? What is the three-dimensional space in which that surface exists? Some physicists speculate about a bulk, a higher dimensional space containing multiple holographic universes, each encoded on its own boundary. We'd be one universe among many, all embedded in a larger reality we can never directly perceive. Others suggest the boundary itself is all that exists. Our three-dimensional experience is constructed by the quantum dynamics on that surface, but there's no outside any more than there's a physical realm where mathematical equations live. Recent work by Sean Carroll at Johns Hopkins and Brian Greene at Columbia University explores these possibilities. Their models suggest the cosmic horizon might connect to other holographic universes through quantum entanglement, creating a multiverse of holographic realities. We may never know what lies beyond our cosmic boundary. The holographic principle suggests that all information about our universe is contained within that boundary. There may be no meaningful question about what's outside, but the search continues. Experiments probing the Planck scale, observations of gravitational waves, analyses of the cosmic microwave background, all might reveal new clues about reality's fundamental nature. The universe has layers we're only beginning to comprehend. We've journeyed from Hawking's black hole paradox through accumulating evidence in quantum entanglement, emergent spacetime, and holographic noise. We've seen how the holographic principle emerged from the mathematics of information and gravity, unified through string theory and quantum error correction. We've explored implications that challenge our understanding of space, time, locality, and reality itself. The evidence suggests something remarkable. Our three-dimensional universe, with all its complexity and wonder, might be a holographic projection from information encoded on a distant two-dimensional boundary. This doesn't diminish reality. It deepens it. We're not less real for being holograms. We're part of an astonishing cosmic computation. Information processing itself into existence moment by moment. The current scientific consensus recognizes the holographic principle as one of the deepest insights in theoretical physics. While questions remain about how it applies to our specific universe, the mathematics is compelling, and the evidence continues to accumulate. Experiments over the next decade improved gravitational wave detectors, quantum simulations, cosmological observations will test these ideas with increasing precision. We may discover that reality has fewer dimensions than we experience, that space and time emerge from quantum information, that the universe is a self-computing hologram written in the mathematics of quantum gravity. Or we may find something even stranger waiting in the equations. The boundaries between what we know and what we imagine continue to blur. The universe reveals itself layer by layer, each revelation more astonishing than the last. We are holographic beings contemplating our own projection, quantum information asking questions about its own nature, the universe observing itself through the instruments of science and the spark of consciousness. Long pause. Reality's deepest secrets might be encoded on a distant boundary we can never reach. Yet everything we are and experience emerges from that cosmic canvas. The universe is vast. The mysteries are endless. The journey continues.